My talk today is based around the extremely large telescope which is now being constructed down in South America. And it is extremely large, as somebody commented. These are some people working down here which will give you a sense of scale. What we're looking at here is, of course, the dome that will house and protect the telescope. The only bit of the actual telescope here that is currently in this drone footage from May 2024 visible is this support here for the main mirror, which had just been installed at the time this video was made. Here's another view from the same video which I like. As you can see, the shadow showing us the conical shape of the mountain with the dome on top where the telescope is sited. And another lovely view with the sun setting a bit lower, and you can see here the dirt track that was the earlier route up to the summit and the tarmac spiralling route that now takes you up to the working area at the top of this mountain. So based around that large telescope, this is the plan for my talk. Why do you want such a big telescope? Why is it there when it was until recently called the European Extremely Large Telescope? And then we'll go and have a little look through the history of the technology of big telescopes, culminating in the Extremely Large Telescope and its mirrors, and along the way looking at some of the challenges and some of the methods used to manufacture the optics for these devices. So why do you want a big telescope? Well, the first reason is obvious, really. If you think about it, the bigger the aperture of your telescope, the more light you can collect. So you can see things which are fainter. And really importantly for the astronomers, you can gather more light from any given object. And it's the ability to do more than just see that there is something there, but to actually split up the light into a spectrum that enables astronomers to determine what a star is made of, or what gases there might be in between it and us, how fast it's moving, things like that. The second reason is not so obvious unless you're an optician. It's a phenomenon called diffraction limiting. And that means that the larger your aperture, the more detail you can see within a picture. And this is illustrated rather well in these two pictures from infrared telescopes, space telescopes. So there's no difference in the atmospheric conditions. The only difference really, they're both working at the same wavelength. The only difference really is the aperture of the two telescopes. The Spitzer earlier telescope has an aperture of 0.85 meters. So what's that, about 30 inches? And the Herschel has an aperture of 3.5 meters, so more than 10 feet. And you can see a vast difference in the resolution and the detail in this picture of the M51 galaxy. So the second question is, why is the telescope being sited there on the far side of the world when it was, as I say, until recently called European, and now that's been dropped to perhaps to get more people on board, but also reflecting the fact that, if you like, other competing telescopes, other large telescopes being built, have decided not to call themselves extremely large. So most of the money and the people still come, and the technology still comes from Europe. There are many things to take into consideration: the logistics of transporting the bits to the site and assembling them there. You want it in a politically stable situation. You need to be able to get access to your telescope, which is a huge investment, of course, for at least you'd want to plan for 50 years or so. You need, for it to work at all, you need supplies of electricity, access roads, you need water for the people who are there to survive. One thing you don't need anymore these days is for the astronomers to be able to get to it. No longer do astronomers, professional ones at least, spend their nights with their eyes glued to eyepieces in order to do their jobs. They are analysing data which is collected electronically and can be sent around the world. But that does mean you need a good electronic data connection. So all these factors would drive you to siting a European telescope in Europe. But there are other factors. One important thing is from Northern Europe, the bulge, if you like, of the planet means that we can't see some parts of the sky. And famously, the flags of Australia and New Zealand depict the Southern Cross, which is a constellation that you can't see from Britain. The overriding consideration, though, is what astronomers call the seeing, how good a view they can get, basically. And this drives you to a site that is high up, simply meaning there's less air between the telescope and the rest of the universe. Also very important is that there should be low moisture levels. Apart from actual clouds that visibly obscure the view, moisture will absorb some of the wavelengths and distort the view more. And another important factor, which means you need to move really away from most of the high populated areas of the world, is the increasing instance of light pollution from street lighting and other outdoor lighting that lights up the sky and obscures our view of the stars. And this has led to the selection of a site in the Atacama Desert. The Atacama Desert is quite a remarkable place. It's the driest place on Earth, apart from the poles, which are dry because the water never becomes liquid there. There are parts of the Atacama Desert where no measurable rainfall has fallen since the Europeans arrived in the area in around 1570. This is because there are mountains to both east and west of the central region that create a rain shadow, and also because up here in the Pacific there's a phenomenon called the Humboldt Current, which causes climatic conditions and means very little moisture comes inland from the Pacific. That's perhaps important for our site because it's not right in the centre of the desert, but in the mountainous region closer to the Pacific coast. In order to prove to themselves that this was a good site, they located measuring equipment not only here but at several competing locations around the world to measure the quality of the scene. And just look at the wonderful star patterns visible from this test site. The Milky Way there and thousands of stars. You can believe it is said that the human eye can see as many as 11,000 stars unaided, and you can start to believe it when you see a sky like that. I went outside the other night when it was quite clear, and I would be lucky to see 100 from here. Another view of the clarity of the site. This is with a static camera, and each individual star is forming a streak due to the rotation of the Earth in this long exposure. And you can see the measuring equipment for monitoring the site as well in this picture. So now, taking a step back, looking at the evolution of telescopes, I found this picture on the corner of an old print I've got. These are astronomers in the days from before telescopes, and they have nothing better than their naked eye and this croix-de-Lorraine sort of arrangement that I presume they were using to measure the angles between the planetary bodies that they were looking at. And they would have had an maximum aperture of about 2.5 millimeters. A big step forward, of course, came with the very first telescope to be turned on the heavens by Mr. Galileo Galilei, who was not only a scientist, an astronomer, but an artisan. And this telescope is understood to have actually been made by him in about 1610. And it has an aperture, a lens diameter of about 15 millimeters. So we've gone up a factor of 6 on the radius. And with this, he was able to see stuff that had never been seen before, important science. Notably, famously, he saw the principal moons of Jupiter. Jumping forward quite a few centuries now, in the first half of the 19th century, in the intervening time, astronomers, according to how wealthy they were, because they were mostly amateurs, there were very few people who could call themselves a professional astronomer. I think a few employed by the courts or high nobility. But anyway, people built themselves telescopes according to their economic means and according to their engineering capabilities. And this Lord Rosse, Charles Parsons, was an engineering entrepreneur who built this on his estates in Ireland. So probably had not very good view with the amount of cloud that you get in Ireland. But this was a 6 foot, 72 inch, about 1.8 meters diameter reflecting telescope. So in the bottom of the tube here is a mirror which focuses the light back up here to where there's an angle placed at a mirror, and a mirror placed at an angle, so that the astronomer, when it's night time, can see from the viewpoint of this gentleman here. The telescope mirror at this time, they didn't know how to deposit a good surface on glass, so this mirror, like most mirrors, if not all mirrors of the time, were polished metal, not the silvered or aluminized glass that we're accustomed to, with significantly lower reflectivity. But he still not only could gather more light, but he could see more detail, as I've said. And this sketch by him is in fact of the same M51 galaxy as we saw in the Herschel and Spitzer images earlier. And he was the first person, important scientific development again, to depict a spiral galaxy. We're now quite accustomed to the idea that galaxies, a lot of them have a spiral formation. But he was the first person to report it to the world of science and astronomy. And this picture also reminds us that at the time photography was in its very infancy, and certainly not applied to astronomy, and any astronomical information, graphical information, was done by the astronomer peering through the eyepiece and drawing by hand what he could see, or thought he could see. Moving on 50 years now, we have another telescope. This is the Yerkes 40-inch refractor. So this is a telescope that uses lenses rather than mirrors, and is significantly smaller than Lord Rosse's telescope, but very important in the history of astronomy. This was taken, this photo, on the occasion of a visit by Albert Einstein, who apparently on arrival in the USA said there were two things he really wanted to see, and one was the Niagara Falls and the other was the Yerkes telescope. I'd also call your attention in this picture to the mechanism here of rotary axes at funny angles. This is needed not only to point the telescope where you initially need it, but to be able to, by just turning one of these axes slowly, to be able to keep pointing at the same place in the sky as the Earth rotates. Another view of the telescope here, so you can see again the proportions of it, the huge length relative to its diameter, which is the big problem with refracting telescopes, and which led, combined with this steering mechanism, to the fact that the viewing point here is going to move up and down a huge amount according to what you're looking at. So not only is this an interesting telescope, but they claim to have the largest lift in the world, as the entire floor of this building moves up and down so that the astronomer can be standing at a convenient height to look through the telescope. Important science from this telescope was greatly enhanced by the fact that astronomical photography now became available, and the data, the images gathered by this could be shared with not only with other astronomers with great accuracy, but also with the public, and capture the imagination of the public. So here we are again with M51, and we can see that Lord Rosse didn't do too bad a job of sketching it. But now we can see a lot more detail and be more confident about the accuracy of the image we've got. Probably, though, what fascinated the public more was the detailed images possible of the surface of the moon. Now moving forward approximately another 50 years, in fact, this is the Hale telescope on Mount Palomar. A big step forward in size. This has a 200-inch primary mirror. So we're back to a reflecting telescope, making it much more compact. In fact, I have a picture like this, a black and white picture, in an astronomy book that I had since I was a teenager, and I supposed that this tube, this cylindrical object here, was in fact the telescope, but the telescope is really this piece here, with a mirror at the back here and a secondary mirror here, a skeletal system supporting the secondary mirror above the primary, and all this mechanism and a big structure around here is again the rotary axes needed to be able to point it in the right direction and maintain it pointing in the right direction. This telescope was a great achievement of technology. This 5-meter disc was the largest piece of glass ever cast at the second attempt by Corning in Pennsylvania in northeast USA. And here it is being loaded onto a train, which processed at a speed comparable to Queen Victoria's train journeys, not exceeding 25 miles an hour, all the way across the states to Southern California, where Mount Palomar is. So a very long journey, stopping at lots of cities on the way for people to admire it. It's at this point worth mentioning the debt that astronomy owes to cookery. There are a lot more cooks interested in purchasing things made of glass than there are astronomers. And so when cooks demand pieces of glass that they can pour boiling water into or place in the oven, the glass manufacturers pay attention and start to create special glasses that can withstand that kind of thermal shock. And it was the existence of Pyrex that made it possible to cast such a large piece of glass. And for astronomers has the additional advantage that the reason Pyrex doesn't break when you heat it is not that it's exceptionally strong. If you drop it on a hard floor, you'll find it breaks quite easily. But it's because it has a low coefficient of expansion. So heating one side of it whilst keeping the other side cool doesn't cause huge strains in the material and make it break. So this low coefficient of expansion means for astronomers that once they've managed to make their piece of glass exactly the shape they want, it will stay relatively stable and won't distort so much in the with the changes of years of the seasons and the weather. So I was rather surprised to be able to find an actual picture of a machine polishing that mirror. I had heard also that a lot of the polishing was done by hand by generations of students from the university down in that area of California. But this took a long time. The glass was cast in 1934 or 35. They started work on casting it in 34, and the telescope went into service in 1948. So that's 14 years, and I don't know that all of that time was spent polishing the mirror, but I think quite a lot of it. Even though the war might well have stopped work for quite a time, it's still a very long time delay between these two phases of the project. But it's important, so we should give a lot of credit. This was well ahead of its time. This telescope remained the largest in the world from 1948 to 1993, so 50 years almost of supremacy. So that then takes us into the 1990s and 2000s, when there's been quite a surge of large telescopes and the new generation of telescopes. We have the 8-meter category telescopes, exemplified by the very large telescopes, set of 4 of them, belonging to the ESO, who are the people who also are building the ELT that I'm basing this talk around. We have the competitors, which are still at the projected stage of if you like, the extremely large telescope, other very large telescopes that are projected, and we have other 8-meter category telescopes, and then the telescopes where they decided 8 meters was definitely the limit for one piece of glass and wanted to go bigger, so they've made the telescopes with their primary mirrors made in multiple segments, like the Gran Telescopio Canarias, which is the current largest single telescope in the world, and is technically in Europe, being on the Canary Islands. So here is an 8-meter primary mirror telescope, one of the VLTs, one of the very large telescopes, and we can see it has some similarities in appearance to the Palomar one, with a structure supporting the secondary mirror, an open structure placed down the bottom here where the main mirror will be hidden. But what draws my attention is that this fills much more of the observatory, because we've got rid of those cumbersome, awkwardly angled rotary axes. Now servo technology has improved so that we can synchronize 2 axes, just a simple altitude here, a pivot line here, and azimuth axis here, which rotates about this axis. So synchronizing those 2 axes, we can keep the telescope pointing in whichever direction we want. And that telescope is situated here. As I said, there are 4 of them on this one site, Mount Paranal, Cerro Paranal, in the Atacama Desert, because just over here is the mountain Cerro Amazonas, where the extremely large telescope is being constructed, enabling some synthesis, some synergy between the 2 projects, reducing the cost of the ELT by being able to make use of some of the facilities like accommodation and engineering support that are already in place for the Paranal telescopes. Also, the water and electricity supplies are already there and don't have to come so far. But an 8-meter telescope is, as I commented, probably the limit for a single piece of glass telescope. Here is the blank of one of the VLTs being transported in Mainz from its Schott factory in Mainz, where it has to go to into France, where it's polished and shaped, taking up 3 lanes of the highway and going none too fast, I imagine. Once it's been finished in France, it then has to be loaded on a ship, transported across the Atlantic, through the Panama Canal, round down the west coast of South America, and I believe it went all the way down to Santiago, when it has a 1,200 kilometre, 800 odd mile overland trip to the site, and not an easy trip either. Here it is preceded across the desert by 3 graders to make the road surface for the lorry to take it to its installation site. And on top of that, there's all the handling challenges of dealing with that when it gets there. So a big adventure every step of making such a huge single mirror. But taking a step backwards, the process of making telescope mirrors, well, there are hundreds of amateur astronomers who make their telescope mirrors in this way. If you just rub 2 surfaces in 2 pieces of glass together with some rotary motion and an abrasive between the 2, you will end up creating a spherical surface between the 2. The curve that forms between the 2 is a sphere, so that makes a good start for your telescope mirror. The ideal shape is usually going to be a parabola, represented here by the black curve, and a spherical curve would be the red curve. So if you stick close to the central axis and have a relatively small mirror, the 2 curves are very close together, and some amateurs might be content with a purely spherical one, though they know it won't give them perfect results. The keener ones will be trying to polish separately after they've made the basic form. Will be trying to polish further out away from the edge to get a closer approach to parabola. And that's much more difficult for them to do exactly the same thing all the way around, and to be able to measure that rather than as compared to the purely spherical form, to confirm that they've got the shape they want. So moving up from the 8-inch amateur mirror to the 8-meter professional size, we're very fortunate that the University of Arizona Mirror Lab are open about their work, and we can see their process here. They start by this gentleman's lining the outside of the mould where the mirror will be cast, with making the wall here out of ceramic material, and then they fill the inside with more pieces of ceramic, these hexagonal elements, and these are cores which are to prevent the glass going where these hexagons are. It goes down into the cracks between these, so that you end up with a honeycomb structure on the back of a smooth sheet of glass that will be formed on top of these. So having filled the whole area with those hexagonal pieces, they now put glass, the raw glass if you like, on the back, on the top of it, and the glass here is all carefully inspected and weighed, so they end up with exactly the right quantity of glass, that's to say the right thickness to their mirror. And when they've done that, then the furnace is closed up and it's heated up so that the glass melts. And this is vastly accelerated in this view. The temperature when glass is practically liquid to flow easily is around 1500 degrees centigrade. That's as hot as melting point of steel. So a pretty serious job to get to this temperature and to build adequate molds and things that will withstand the temperature. And what we see now, we're partway through the melting process. There are bubbles coming up as air is replaced by glass in those in the honeycomb elements. And in the next, once we resume movement here, we'll see the level here dropping. They want it to stop 3 divisions below this number 5, to dropping down to its finished point. So there we are, we see more bubbles coming up and we see it settle at the desired level. And now it's inside this furnace, which they then, in a process unique to Arizona, I think, spins round, which is quite an achievement at that temperature, with cameras, heating elements, and so on all inside there. It spun round so that, just like the cup of tea when you stir it up, the middle is lower down than the edges, and this actually gives them a starting point of a parabola on the surface. So if they cool it whilst it's still spinning, just cool it enough for the glass to solidify, and then they carry on with the process. Just another view of the glass coming down into position as it melts. A reminder that we've got all these hexagonal elements in there, and then that cooling and heating process that we've just seen takes several days or even a week or two, but then they, before they crack open the mold, they are very slowly letting it come back to room temperature, and they leave it for several months before they crack the mold open again. And then we've just seen here the process of the huge blank being lifted out of the furnace, transported across to this big fixture so that it can be tilted on its edge. Now they put a cover in front of it to retain the residue, as they have the task now of removing all those hexagonal elements and the bits that hold them in place, to get the glass blank to just glass. Then it's placed face down for this machining polishing operation, which, if the narrator on their video is to be believed, they then spend a whole year polishing the back face, not the side they're going to use optically, a whole year polishing the back face before they turn it over again and start work on the front face, which of course is much more demanding and requires much more accurate form to be produced. Now here again is another process unique to Arizona. Instead of just using polishing and grinding tools on the blank, they have this big polishing tool which has all these actuators on the back so that it can be continuously bent, so that the underside of it makes the shape that they want to produce on the glass, and it's continuously distorting itself so that it's polishing the right form onto the glass mirror. Here we see quite interesting details of the process, including what the underside of the lap looks like as it's coming off the edge of the component. And then they finish with a lighter polishing, but a less sophisticated polishing process that I guess is just improving the quality of the surface rather than trying to modify its form. So that was Arizona making an 8-meter telescope mirror. Let's jump back now to the ELT, and here is the road to the ELT zigzagging up the hill a few years ago now. The next stage was in 2015. That a cloud of dust and smoke is the first explosion as they blast off the top of the mountain to make a flat area in which to work. Right, here we are with a view of the extremely large telescope, and outwardly it looks very similar to the very large telescope that we saw before, but this is much bigger. The almost 40-meter primary mirror here is nearly 5 times the diameter, 25 times the area of the VLT mirror. And that involves some attendant difficulties. For instance, it again has a azimuth axis here which rotates the whole lot, but that axis weighs 2,800 tons. Then there's the altitude axis here, as we had before. The instruments are sighted right on that axis, so they don't have to change position as the telescope is moved around. It's always going to be directing its light out to the instruments without having to move the instruments themselves. We'll look at the positions of mirrors in this in a moment. The other thing to note here is these yellow tubes are its lasers. Why does a telescope need lasers? Well, we'll see in a few slides' time. So here we have really the optics with very little else. The primary mirror M1, 39-meter diameter, made of 798 hexagonal segments. That's a lot. When you would think that making one mirror that size was taking a year or so, not so very long ago, the scale of this project starts to become evident. The secondary mirror is again a record breaker with a 4.2 convex mirror, the largest ever convex mirror made. That sends the light down to M3 here, up to M4. M4 is flat, but has some very special properties that we'll be looking at in a minute. And that sends the light out to M5, which in turn sends it on to the instrument platform. And this slide is showing us the comparative sizes of telescope mirrors through history and of the largest telescopes. So here is the extremely large telescope. Here are the other two giant telescopes that are currently live projects or actually under construction or not. The 8-meter glass mirrors, these green ones here, represent the 4 VLTs that we've seen, and here's another one from the same school. Then we have the Magellan telescopes and large binocular. These are made by Arizona, 8-meter class telescopes. And we have the first segmented telescopes here in the Keck telescopes on Hawaii, American ones, and the Gran Telescopio Canarias that I've mentioned before, the current largest single telescope. Then looking back over here, we would find the Hale Mount Palomar telescope, 5 meters here, and the Yerkes 40-inch lens that we saw a picture of. So discounting these other two very big telescopes, it's reckoned that the primary mirror of the extremely large telescope is bigger than all previous telescope primaries put together. And to revise the geometry a bit, the shape we're after is something like the black line here, a parabola, and we obviously can't build machines big enough to swing around this central axis in order to make the pieces out here. that's one of the advantages and one of the challenges of making the thing of a lot of hexagonal segments. We have to take the geometry that we find here and be able to use a mathematical description of it and a coordinate transformation to place it in the center of our work zone, and then have a machine that's capable of a fully versatile range of movements to describe more or less any shape, so that we can reproduce the shape we need here on a much smaller than 40 meters machine. And Kodak Special Optics division realized that they were going to need such a capability as far back as in the 1980s, and commissioned from us at Cranfield Precision Engineering the off-axis grinding machine with a 2,500 millimeter square, 2.5 meter square capacity. And here am I in a younger manifestation operating it. On 20 years or so further on, the Cranfield University, in the form of Professor Paul Shaw, saw the commercial and industrial scale optic manufacturers' demand that would be posed by the proposed extremely large telescope. And so he at the university commissioned us to help them build this machine, which really does the same job as the previous machine, but as you can see is considerably more compact, partly by the use of newer technologies and partly because it's much less versatile. It's very much dedicated to this particular size of about 1.4 meter hexagon, demanded by the proposals for the extremely large telescope. And here is the machine doing a bit of grinding. This was actually used to make test segments supplied by and returned to, after making and polishing, the ESO for their development work. So these two machines we've seen above are grinding machines with a tool, the grey tool is represented here, which might have different forms, but basically is going to have a curved end to it. And this is a tool of fixed geometry, and we have to know very accurately what that geometry is if we're going to make a part accurately. But what it's going to do is to grind a groove across the workpiece, which is the green item here, and it can only grind a series of lines across the part. It can you can put the lines closer and closer together, but there will always be a series of cusps like this between the lines. But if we've done our work with the geometry and the machine controls and so on well, then the bottoms of these grooves will be very accurately the form that's required on the finished part. So with these cusps, we then need to do some polishing, also to improve the finish of the surface finish on the part to the high level that's required for a mirror. So we moved then into a polishing process, which is quite different, although you might first think that it had some similarities. If we had a polishing tool that's say this kind of shape with a flat bottom, if that were a hard tool, then we'd only be able to make flats on the part, and we'd just be doing the same thing as the grinding machine has done. So this has to have some ability to conform to the surface so that it's doing a polishing instead of a grinding operation. And the amount of material it removes then is not exactly defined by you moving this across the part, as it was with the grinding machine. It varies with the shape of the tool, obviously, the stiffness and the material that it's made of. With the abrasive you use, the tool is for polishing is probably not going to be abrasive itself. It will instead have a slurry containing a abrasive grit between it and the workpiece. Then it also depends on the speed of rotation, the pressure and the dwell time, how fast it moves across the component, or whether it stops in one place, will depend on, that will vary the amount of material removed. And we sum up a lot of those characteristics into what they call an influence function, and say that typically this tool will remove more in the middle and gradually less as you get to the outside edges of the tool, rather than removing an exact shape. So if it comes down onto this rough surface, you might think, well, we want to remove these high points, but in fact it will also be removing some material from the rest of the part as well. But because the pressure is higher where these points are, it will eventually smooth this surface out, but with the whole level reduced somewhat. If we're then going on to something where there is either a surface finish or a shape modification required, so the surface finish is actually roughly comparable in size with the polishing tool, then we have a different sort of challenge in that we start trying to remove this bump, but we're taking material off here as well, and we can end up, for instance, generating a shape that's the opposite of what we started with, so we've still got the same ripples but moved across, or we might end up with something that creates more finer ripples, but we have very great difficulty polishing them out with a tool that covers a larger area. And some very high-powered mathematicians have worked on algorithms for the problem of actually creating the shape you want using the influence functions of polishing tools. And here is some polishing taking place at Safran, who are the people who actually have the job of making the mirrors for the ELT. One form we've just seen. Here's another method of polishing with the peripheral wheel rather than the face of a cylindrical tool. A further method which is sort of equivalent to polishing in some ways are the plasma jet, or in this case iron beam machining techniques, which are used by both Kodak, or Kodak's successors now as they've sold off that activity, and Safran. This is iron beam machining, and it's similar to polishing in that it covers a fairly large area and takes off a greater quantity in the middle and a lesser quantity around the edge. So again, it has some of these challenges of working out a path that will actually leave you with the shape of piece that you want. You don't get to see this very much because it all takes place in the dark in a vacuum chamber. But I did find this slide from Kodak a good many years ago in a presentation to students. So having made the shape on your hexagonal elements, and these by the way are blanks without the shape on them, you might think there you are, all you've got to do is put together this big jigsaw puzzle. But no, this is a test rig for the supporting systems, and this is what the back of each of those hexagonal elements looks like, with a whole load of elements, sensors for the edge position and elements for holding it without distorting it, and for pushing it this way and that. And these are needed continuously in operation because as the whole mirror tilts, even once you've got it aligned, as the whole mirror tilts, the direction of the force of gravity will change, and the whole thing would distort if you didn't keep pushing it back into shape with all these systems. So the whole thing is extraordinarily complicated. A final view inside Safran of the M1 segments accumulating in their factory that they've built just for the purpose of working on these elements. They now have all of these delivered, all the blanks delivered by Schott, making them out of Zerodor. I should mention these European mirrors are made of Zerodor, which is a further step beyond the glass that Arizona and Mount Palomar and Corning were using. Again, cookery, the cooks, not content with having heat resistance utensils, decided they wanted worktops with red hot elements buried in them, which put a further demand on the possibilities of glass. So vitroceramics like this were developed with more or less zero coefficient of expansion, so that you can heat these up very greatly, or for the astronomer's purpose they remain extremely stable regardless of the temperature changes in the environment. And 798 of these in the mirror, but they want some spares. And the mirror has six-fold symmetry, so there are actually 133 different shapes on the surfaces of these hexagons, 6 of them in the mirror and a 7th one which is a spare. So there are in fact 931 total number of these hexagonal elements. So back to the construction site. Here's a view of the tower, which you may recall it has to hold the M3, 4 and 5 mirrors in the middle of the primary mirror. This is obviously before it was assembled into the main telescope. And up here there will be mounted the flat M4 mirror. The M4 mirror that we said we'd talk about later. And here we see the support for one petal of the M4 mirror. And here we see the M4 mirror glass piece. These are very thin, very flat sheets of glass. And that piece with multiple holes in is to contain multiple actuators and sensors, so that they can put very slight distortions onto the face of this mirror. And they want to do that because even this wonderful site that they found with the dry atmosphere and not too much atmosphere above it still has too much atmospheric distortion to fully use the capabilities of a 40-meter telescope. They still want to correct for the distortion of the atmosphere, and this is something they didn't know that would be technically feasible when they started the project. The whole success of the project depended on it, but they had to start the project without knowing whether they could do it or not. But now the principle has been proven that you can have a look at you can point your telescope at the sky. You can look at an object in it, and as long as in the same field of view you have a star will be a single point, whereas a galaxy or dust cloud or anything will be a more vague structure. So they can focus on the single point, and if they can distort a mirror sufficiently to see that star as a single point, then they know the rest of the picture is also sharp and telling them what they really want to see. The problem is, once you've overcome that slight challenge, you can only do it if there's a star in the same field of view as the object you're looking at, which is not generally the case. So here we can see on the Mount Paranal observatories a laser being shone up into the sky. They're not trying to shoot down the stars, and this laser is quite weak. You wouldn't be able to see it with the naked eye, but this is a long-term exposure. The laser is shone up into a layer of the atmosphere 50 miles above the Earth, and thus really above virtually all the atmosphere, where there are sodium ions which fluoresce when the laser hits them, and that creates an artificial guide star which they can use for this adaptive optics technology, as it is called. So this is the experimental procedure on Paranal, which will then be an essential part of the extremely large telescope. And I should say here the photograph, the camera is stabilized to the stars, but that means that in the time exposure the observatories themselves are moving, so these are blurred whilst the stars are sharp. This slide is showing the effect of the adaptive optics. Here is a view as it would be from the Hubble Space Telescope, so no atmosphere in the way to distort the image, but the limited capability of the telescope gives you this kind of image. Then the very large telescope with adaptive optics can see this kind of quality of a view of the same thing in spite of the presence of atmospheric distortion. And going a stage further into the extremely large telescope, you can see a further improvement in the detail. So that brings to the end of my talk with this wonderful picture of the construction silhouetted against the full moon. So we've just looked at some of the technical challenges and how they're overcome for the ELT, and a bit of the evolution of telescopes that will lead, we hope, to further astronomical discoveries.